Black holes. The name conjures images of cosmic vacuum cleaners relentlessly sucking up everything in their path. But is this terrifying picture accurate? Not quite. While black holes are powerful objects, their reputation as insatiable devourers is a bit overblown. The reality is far more nuanced and, dare I say, even more fascinating. To understand why, we must first journey into the heart of a black hole, exploring its formation and the true nature of its gravitational pull. Only then can we appreciate the crucial role these enigmatic objects play in the grand cosmic ballet. Prepare to have your mind stretched as we delve into the captivating world of black holes and separate fact from fiction. Imagine a star, much more massive than our sun, nearing the end of its life. This star, a supergiant, has been burning brightly for millions of years, fusing hydrogen into helium in its core. But now, it has reached a critical point in its life cycle. The nuclear reactions that have sustained it for so long are winding down. It has exhausted its nuclear fuel and can no longer support itself against its own gravity. The once vibrant and powerful star begins to dim, its outer layers cooling and expanding. The core, however, is a different story. It becomes a dense ball of iron, unable to generate the energy needed to counteract the immense gravitational forces pulling it inward. The core collapses inward, crushing the star's mass into an incredibly small space. This process happens in a matter of seconds, but the effects are monumental. The outer layers of the star are blasted away in a supernova explosion, one of the most powerful events in the universe. The core, now a neutron star or black hole, is left behind. This catastrophic implosion creates a region of space-time where gravity is so intense that nothing, not even light, can escape. This region is what we call a black hole. The formation of a black hole is a dramatic and violent event, but it is also a natural part of the life cycle of massive stars. This, my friends, is a black hole, a place where the laws of physics as we know them break down. The black hole's gravity is so strong that it warps space-time itself, creating a singularity at its center where density becomes infinite. It's a region of extreme density, a singularity, shrouded by an invisible boundary called the event horizon. The event horizon is the point beyond which nothing can return. It's like a one-way door to oblivion. Once something crosses this boundary, it is lost to the black hole forever. Think of the event horizon as a point of no return. It's the ultimate boundary beyond which the gravitational pull of the black hole becomes irresistible. Anything that crosses this line is doomed to be pulled into the singularity where it will be crushed to an infinite density. Once you cross it, there's no turning back. The gravitational forces are so extreme that they stretch and compress objects in a process known as spaghettification. This means that anything falling into a black hole is stretched into a long, thin shape like a piece of spaghetti. The gravitational pull inside the event horizon is so strong that even light, traveling at the fastest speed in the universe, cannot escape its clutches. This is why black holes appear black. They emit no light and are invisible against the backdrop of space. We can only detect them by observing the effects of their gravity on nearby objects, but here's the catch. A black hole's gravitational influence isn't infinite. It doesn't extend indefinitely into space. The gravitational pull of a black hole decreases with distance, just like any other object in the universe. This means that objects far enough away from the black hole can orbit it safely without being pulled in. It doesn't reach out like a cosmic vacuum cleaner, indiscriminately sucking up everything in sight. The idea that black holes are cosmic vacuum cleaners is a common misconception. In reality, a black hole's gravitational pull is only strong near its event horizon. Beyond that, its influence is similar to that of any other massive object. Its reach is determined by its mass, just like any other object in the universe. The more massive the black hole, the stronger its gravitational pull. But even the most massive black holes have a finite reach. Understanding this helps us appreciate the true nature of these fascinating cosmic objects. We all experience the pull of gravity every day. It's a force so familiar that we often take it for granted. Whether we're walking, standing, or even jumping, gravity is the invisible hand that keeps us tethered to the ground. It's the force that keeps us grounded on Earth. Without it, we'd float aimlessly into the void of space. Gravity is what gives us weight and keeps our feet firmly planted on the ground. But how does Earth's gravity compare to that of a black hole? The Earth, with its relatively modest mass, exerts a gravitational pull that is strong enough to keep the Moon in orbit, and to hold our atmosphere in place. But a black hole is a different beast altogether. Let's imagine replacing our sun with a black hole of the same mass. This thought experiment helps us understand the nature of gravity and the unique properties of black holes. What would happen to Earth? Would it be sucked into the black hole? Or would it continue its cosmic dance around this new, mysterious object? The answer might surprise you: absolutely nothing. Despite the black hole's fearsome reputation, the Earth would continue to orbit the black hole just as it orbits the sun now. The Earth would continue to orbit the black hole just as it orbits the sun now. This is because the gravitational pull that keeps Earth in orbit depends on the mass of the object and the distance between them. This is because the strength of gravity depends on two things: mass and distance. The gravitational force is directly proportional to the mass of the objects and inversely proportional to the square of the distance between them. Since the black hole has the same mass as the sun, and Earth would maintain its distance, the gravitational pull would remain the same. The Earth would continue its orbit, unaffected by the change in the nature of the central object. The difference lies in the concentration of that mass. While the sun's mass is spread out over a vast volume, a black hole's mass is concentrated into an incredibly small space. Imagine squeezing the entire mass of the sun into an area the size of New York City. This gives us a sense of the incredible density of a black hole. That's the incredible density of a black hole. This extreme density warps space and time around it, creating a gravitational pull so strong that not even light can escape from it. This extreme density creates an exceptionally strong gravitational pull in its immediate vicinity. Objects that venture too close to a black hole are pulled in with such force that they are stretched and compressed in a process known as spaghettification. Spaghettification is a dramatic demonstration of the power of a black hole's gravity. As objects get closer to the black hole, the difference in gravitational pull between the near side and the far side becomes so great that they are stretched into long, thin shapes. The boundary around a black hole, known as the event horizon, marks the point of no return. Once an object crosses this boundary, it is inevitably pulled into the black hole, unable to escape the immense gravitational pull. Black holes are fascinating cosmic phenomena that challenge our understanding of physics and the nature of the universe. They are a testament to the incredible power of gravity and the mysteries that still await us in the cosmos. So while the Earth would continue to orbit a black hole of the same mass as the sun, the true wonder lies in the unique and extreme properties of black holes themselves. They remind us of the vast and awe-inspiring universe we inhabit. So, if black holes don't act like cosmic vacuum cleaners, why do things get pulled in? The answer lies in the nature of gravity, and the immense gravitational forces that black holes exert on their surroundings. Imagine a spaceship venturing too close to a black hole. The gravitational pull it experiences is unlike anything we encounter in our everyday lives. As it approaches, the gravitational pull on the side of the spaceship closest to the black hole becomes significantly stronger than the pull on the far side. This creates a dramatic difference in force across the length of the spaceship. This difference in gravitational force, known as tidal force, stretches the spaceship. The closer it gets to the black hole, the more pronounced this stretching becomes. The closer it gets, the stronger this stretching becomes, eventually ripping the spaceship apart. This phenomenon is often referred to as spaghettification, where objects are stretched into long, thin shapes. This process is not limited to spaceships. It applies to everything, even light itself. The gravitational forces near a black hole are so intense that they can bend light, causing it to spiral inward. The event horizon marks the point of no return. It's the boundary around a black hole beyond which nothing can escape, not even light. Once an object crosses this boundary, the black hole's gravity becomes inescapable. The object is pulled inexorably towards the singularity at the center of the black hole. It's a one-way trip to oblivion, a journey from which nothing, not even light, can return. The immense gravitational forces ensure that anything crossing the event horizon is lost forever to the depths of the black hole. Black holes are fascinating and mysterious objects in our universe. They challenge our understanding of physics and push the boundaries of what we know about gravity and spacetime. Scientists continue to study black holes to unlock their secrets. By observing the behavior of matter and light around them, we can learn more about these enigmatic objects and the fundamental laws of the universe. One of the most exciting areas of research is the study of black hole mergers. When two black holes collide, they release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time. These gravitational waves can be detected by instruments on Earth, providing us with valuable information about the properties of black holes and the nature of gravity itself. Black holes can also emit powerful jets of energy which can be observed across vast distances in space. These jets are created by the intense gravitational forces and magnetic fields around the black hole. The accretion disk, a swirling mass of matter that orbits the black hole, plays a crucial role in the formation of these jets. As matter is pulled into the black hole, it heats up and emits radiation, which can be detected by telescopes. Black holes are not just isolated objects. They are often found at the centers of galaxies, including our own Milky Way. These supermassive black holes can have masses millions or even billions of times that of our Sun. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, is a prime target for astronomers. By studying it, we can gain insights into the formation and evolution of galaxies. In conclusion, black holes are one of the most intriguing and mysterious phenomena in the universe. They challenge our understanding of physics and continue to captivate the imagination of scientists and the public alike. As we continue to explore the cosmos, black holes will remain a key area of research, offering us a glimpse into the most extreme conditions in the universe and the fundamental nature of reality itself. The process of being stretched and torn apart by a black hole's intense gravity has a rather amusing name: spaghettification. Picture this. As you fall into a black hole feet first, the gravitational pull on your feet becomes significantly stronger than the pull on your head. This difference in force stretches your body, elongating it like a strand of spaghetti. The closer you get to the singularity, the more extreme this stretching becomes. Your atoms themselves would be ripped apart, leaving nothing but a stream of subatomic particles. Spaghettification is a consequence of the extreme tidal forces present near a black hole's singularity. It's a rather dramatic illustration of the power of gravity and the bizarre effects it can have on matter.